Hey, what's up YouTube? In today's video I'm going to talk about how I achieved this cool little boat simulation. The thing is, this project is quite advanced and there's a lot to talk about. It can be broken down into 3 separate systems. There's a Niagara driven buoyancy system, a scene capture driven foam system, and a somewhat complex Niagara driven splash system. And so I thought it'd be best to make 3 separate videos, one for each system. Thus, in today's video I'm going to explain how I built a buoyancy system using Niagara. But first, some context. Why would you use Niagara to do this? Isn't Niagara a particle system? Okay, so you probably know that there are a million ways to create a water shader, right? Gerstner waves, FFT simulation, some noise textures that you scroll in X and Y, Flipbooks, the list of techniques goes on and on, right? Now, having made a neat water shader is great, but that's only the tip of the iceberg really, and there are many more things to consider, like buoyancy. Being able to sample the wave height at any given world location to compute and apply buoyancy forces and make an object float is most often required and is most often complicated. You see, all these water shader techniques I just mentioned are great, but they all have one thing in common. They all are entirely computed on the GPU to display its vertices, and they all likely rely on textures and data stored on the GPU as well, and so the CPU is unaware of that. And yet, most physics engines are entirely CPU driven, so buoyancy forces have to be computed and applied on the CPU based on quote-unquote wave data that is on the GPU. What's the solution then? Well, you could do a direct readback or a blocking task. It has many names, meaning you could force the GPU to compute and send whatever data to the CPU right here, right now, like say a wave height, and based on it compute on the CPU a buoyancy force. The thing is that is extremely slow. In a nutshell, the CPU and GPU both do their own thing at their own pace. And so if the GPU were asked to immediately send data to the CPU, it would need to, well, stop what it's doing and get in sync with the CPU to dialogue with it. That induces what you may call a pipeline stall, and that's really bad. So one solution is to use an asynchronous readback or a non-blocking task. Again, it has many names. Now, if the GPU were asked to send data to the CPU, it would do so, but at a convenient time. And that does not induce a pipeline stall. But yes, one of the drawbacks of an asynchronous readback is that you do not get what you ask for immediately. Usually though, the delay is around 1 or 2 frames, so it's more than fine for most use cases. The other downside is that it's usually not straightforward to implement, and as far as I know, in Unreal Engine it pretty much requires C++, and there's not a lot of documentation on the subject, so be prepared to get your hands dirty. However, that was true until Niagara came along, because thanks to Niagara it's now possible to super easily perform asynchronous readbacks. Now, it may not be as optimized as, say, a complete custom solution you'd build in C++, I'm not entirely sure honestly, but from my test it seems to be definitely performant enough to be a viable option, and that is what I'm going to demonstrate today. Now, I'd like to mention there's a second way to approach this whole buoyancy problem. Yes, asynchronous readback is one solution, widely used in the industry, but what if you could just avoid any kind of dialogue between the GPU and the CPU? You see, for some math-driven water shaders, such as FFT or Gerstner waves, it's totally possible to do the exact same math on the CPU and compute the wave height without having to request anything from the GPU. And that's what UE does in its water plugin. Gerstner waves are rendered based on a set of parameters on the GPU to display that tessellated water mesh, right? And those waves are also computed on the CPU using the same exact parameters to get the wave height at a bunch of discrete locations and compute buoyancy on the CPU. That solution, however, may only work with a purely mathematical water shader, and it introduces some CPU overhead, but you at least do get the wave height without any kind of delay. Some techniques, such as FFT, may also be quite tedious enough to set up on the GPU that you may not want to rebuild a CPU solution. So as usual, some pros, some cons. Alright, now before actually getting started with the video, a couple of disclaimers. The system I'm about to demonstrate relies on Niagara, but also on quite a bit of Blueprint, and because of that, performance isn't great. It is definitely usable for a minimalist project, but it isn't scalable as is. However, it should be pretty straightforward to translate the performance-heavy Blueprint part to C++, and that pretty much solves that issue. Although I consider this system to be quite experimental. It certainly seems to do the job fine enough, and in my opinion is totally a shippable solution for a minimalist indie game. Anything with a bigger scope though, and it certainly would have to be battle tested first. So I don't guarantee this to be a bulletproof solution, okay? Moreover, this system is by no means a replacement for UE's buoyancy system, which is plenty capable and performant. That system is however tied to UE's water system, which is Gerstner waves based, and one huge benefit of the technique I'm about to demonstrate is that it pretty much works with any kind of water shader, so that's kinda sweet. Alright, so in this video I'm first going to demo that buoyancy system I just released on my Patreon and explain how to set it up, right? Then I'll do some kind of hybrid between a step-by-step tutorial and a breakdown to actually show you how to build such system. Sounds good? Let's get started then. So, this project comes bundled with 4 demo levels. They all demonstrate the buoyancy system in a very similar manner. There's a boat you can control and there are some floating objects around you. The first level showcases an extremely simple example with a water shader that is simply vertically offset with a simple sine wave. The second level uses Gerstner waves generated procedurally. The third level makes use of that FFT height flipbook method I showcased in a previous video. And the fourth and last one showcases Gerstner waves baked into Flipbooks authored with that tool I showcased in a previous video as well. So let's assume the following scenario. I have a very basic water shader that uses Gerstner waves. Now this isn't a tutorial on Gerstner waves, so I'll skip over that part. And I have a very simple boat mesh and I want it to float. First step is to create a blueprint and add that boat as a static mesh. Its simple collision must be properly set up. Here I used a bunch of custom convex shapes to approximate its shape, but you could start with a simple box collision. Then here I may want the mass in kilogram to be automatically computed by Unreal Engine based on that collision volume, or I can override it. It's going to play a critical role in how much buoyancy force to apply, right, and how effective linear and angular drag are, which are also 2 settings I may want to tweak. Also, there's some form of drag built in this buoyancy system, so it's not technically needed, but still, those are 3 parameters I may want to tweak to get the desired feel and behavior from the physical simulation, okay? Then it's probably best to set that mesh collision profile to physics actor. Also, 2 small tips. 1. Lowering its center of mass might help make the boat be more stable and less prone to tipping over. 2. Creating a physical material that has no friction might help make that boat slide against obstacles and possibly the ground as well, if ever the water level is quite low, which might lead to a better user experience. Now, I could enable simulate physics here, but it's not a requirement, because it will be turned on anyway by this buoyancy actor component I then need to add. It comes with a bunch of important settings, but more on that in a second. I also need this blueprint to implement this blueprint interface, which provides 2 very simple functions. One is used to forward the primitive to simulate, and the second function is used to forward the list of pontoons, so let's create an array and make sure it's plugged in here. Then turn on these 3 options and place as many pontoons as I need. You usually don't need a lot, here I'm going to add 7, but you could try with just 4 to begin with. The more you add though, the more expensive the simulation is. Now let's tweak this buoyancy component. The first and most important thing to do here is to set the Niagara system to use to perform asynchronous readbacks. You see, each of these 4 demo levels have all these buoyancy components configured to make use of a specific Niagara system, O1 for level O1, O2 for O2, and so on. These Niagara systems are all based on a template provided by this plugin, which you can just copy and paste and modify to your likings. And it's quite easily done. All you need to do is to implement a method to sample the wave height and normal at a given world position here. So assuming my water shader uses Gerstner waves generated via this custom HLSL node, well, I can pretty much just copy and paste that entire HLSL code in Niagara and use the same wave parameters, and that's it. But I'll have a better chance at explaining this in greater details during the breakdown, okay? And really, that's pretty much the only thing you need to change in this emitter. Now that it is set here, I may then hit play. Depending on the mesh mass and the way you set up pontoons, it might not float at all or bounce like crazy. There's likely quite a bit of fine-tuning to perform to get the desired behavior, okay? So let's go over the available settings. Here I may choose to enable buoyancy right away upon begin play. Offset acts as an overall Z offset for all pontoons, so rather than changing the Z component of each pontoon individually, I may do that here. Apply wave normal, if 0 then buoyancy is strictly vertical, if 1 it's in the direction of the wave normals, which isn't physically correct, but that may help fake some water flow and add some extra sideways movements, which I personally like. Now radius is quite an important setting. First, let me enable the debug view. So each pontoon is essentially a sphere, and the buoyancy force at that pontoon is computed based on how much of that sphere volume is submerged, meaning how much water is displaced by it. So this radius obviously increases each pontoon's volume and so increases the buoyancy force they each can generate, okay? Now it might make that boat levitate above water if pontoons are too big, right? But then you can play with that offset value to fix this. Snap is an experimental feature to try and guess the best resting location and rotation on the water surface when buoyancy is just getting started, which is something that always annoys me with buoyancy systems. You usually have to place objects in Z quite arbitrarily and let them fall first, which isn't great, and so this is an attempt at fixing this issue. It's not perfect though. Moving on, force coefficient acts like an overall multiplier to the buoyancy force, and max force is quite straightforward. Here are also quite important values, and these will need to be tweaked depending on the mesh's mass. These two settings prevent the mesh from bouncing on the water by dumping the vertical force when a pontoon is in water. Drag is also extremely important. There's angular drag, the more you add the more stable that mesh is, rotation-wise, but then it also gets increasingly harder to turn. These settings are per pontoon, so the more pontoon you add, the more angular drag is applied, right? Same for linear drag. This acts as a brake to mimic how difficult something is to move in the water. So, for a mesh of a given mass and volume, and for a given amount of pontoons, there's likely some fiddling around to do with these values to find the best buoyancy behavior, but that's pretty much it. Having set up this boat, I can do the same thing with, say, a plank. So again, make a blueprint. Make sure that mesh has collisions. Add the buoyancy component, select the desired Niagara system, and tweak that component's settings. Then implement the buoyancy interface to forward that mesh, and the list of pontoons, and that's it. Now, each pontoon comes at a somewhat high CPU cost because it's all done in Blueprint, but more on performance in a minute. Thus, you likely don't want too many pontoons simulated all at once, and so you may want to enable/disable buoyancy on actors based on proximity. You see, these planks and crates are configured to not activate buoyancy upon start. In this pawn blueprint, I then have a volume, and when those planks and crates overlap with this volume, I just get their buoyancy component to call those enable and disable buoyancy functions, right? And that volume is large enough so that from this point of view, that happens outside this view. Also, when buoyancy is disabled for a particular actor, it will freeze that actor in place and disable physics, okay? So it will kinda levitate in air. And so when enabling buoyancy again for that actor, you might want to snap that actor on the water surface right away. The very last thing I almost forgot to mention, for now I assume the water is at 0 in the inward space, but obviously it might not. All you have to do is to update this material parameter collection, water altitude parameter in Blueprint, and you should be good to go. So let's try 300, move that water plane up by 300 units in Z, and sweet, it's working. And voila for the demo. All in all, I think it's quite a simple yet elegant system to use. Now let's get technical and see how it was built. Alright, for once on my YouTube channel, I'm going to go over the basics with a hopefully simple step-by-step tutorial. So first I'm going to create an empty Niagara system, add an empty emitter and set it to GPU like so. Then create an object variable named, say, blueprint. Then I may also create a boolean named, say, bexport. Cool, then create a blueprint actor, add a cube, maybe tweak its scale, like so. Then turn on simulate physics, and add that Niagara system I just created as a component. On begin play, get that Niagara component and update its object parameter named blueprint, and that is going to point to this blueprint actor, because I want this blueprint actor to receive readbacks, right? I may also want to update its boolean variable named bexport and set it to true right away. Okay, having done that, I then need this blueprint to implement that Niagara callback interface, which allows me to implement this event, okay? Now let's configure Niagara to actually export data. This is quite simple. During particle update, add this exporter module. Make sure to set this blueprint variable here, same for its export boolean. You may also want to limit the tick rate of this export module like so. I chose not to here, but you do you. Now I will admit I haven't investigated these settings that much. I have a gut feeling it's best if I set this to per particle here, but I also have a gut feeling that for just a few particles this is unlikely to play a huge role in performance, so meh. I was a bit lazy here, don't mind me. Anyway, cool, now as long as this boolean is true, Niagara will export those two vectors and this float to this blueprint per particle. In that blueprint, using this interface event, I may then loop through each particle's data and do something with that data, right? Note that these variables are named position, velocity and size, but don't pay attention to that. Just think of this struct as a way to pack 7 arbitrary floats, whatever they may be, right? 3 floats in that vector, 3 in that one, and 1 last here. 7 floats isn't that much, so it's a bit of a limitation sadly, but thankfully here it's going to be plenty enough. Now this Niagara emitter is still empty, there are no particles, so there's no data to export. So just to demonstrate it's indeed working, I'm going to spawn a few particles here and there, maybe apply some noise forces. This isn't important. I just want to have particles moving and export each particle's position and maybe velocity as well, why not? In Blueprint, then loop through the exported data and draw debug lines. Cool, it is indeed working. Now if I lower the frame rate, you may notice that those debug lines are lagging behind a bit, and that's that 1 or 2 frames delay you get with asynchronous readbacks. Nothing you can do about it, that's the price to pay for sampling data on the GPU for cheap, it's asynchronous. Now let's get rid of that logic, because the goal is to implement a buoyancy system, right? So ideally, I'd have my boat or whatever buoyant object, and I'd like to compute the wave height at what's usually called pontoons. So just like I explained during the demo, I'm going to make an array of vectors in Blueprint. And one as well in that Niagara system. Then the idea is to spawn as many particles as there are entries in that array, which is easily done. Use a spawn burst module, get that array's length, and voila. Although at this point I probably want to make sure this emitter doesn't loop. Now in Blueprint, let's update that Niagara's array to be a copy of this actor's pontoons array. The thing is that Niagara system may already have processed that emitter spawns tag by the time I update this list, so assuming this vector array here is empty by default, it likely spawned no particle at all. So I think the best course of action here is to simply reinitialize that Niagara system once having updated its array variable. This will process the emitter spawn event once again and ensure the correct amount of particles is spawned. Cool, now assuming I added a number of pontoons in that blueprint array, I should have a matching number of particles in that Niagara system. Next I want to sample the wave height at those pontoons positions, so I'm going to add a custom module in the update stack, add a vector array input and use the execution index to get one of its entry. Again, I spawned one particle for each entry in that array, right? So I can just get the particle index to read the desired index from that array. And that array contains each pontoon's location but in local space, because this list just describes a list of offsets from this actor's origin, right? So I need to transform that location from local to world space. For this to work though, I must ensure this Niagara component is actually parented to this mesh, so its transform matches this mesh transform. Back in Niagara, I may want to write this position as a particle parameter, then add a sprite renderer, override its position to double check that I do indeed have one particle per pontoon in world space. Cool, now all I have to do now is use those pontoons' world positions to sample the wave height. And this is where you may want to do things your own way, depending on the technique you use to create your water shader. So let's start with a basic example. Here I created a super duper simple water material. It's a plain opaque material displaced in Z based on time and world position to create a simple sine wave. And I'm going to take one step further and fix the normals like so. I'm going to do the same exact thing in Niagara, use the same exact parameters, and voila, I have the same exact vertical offset and normal. Now, two important things. By default, cosine and sine in materials all have a period of 1, so it's neither in degrees nor in radians. So I'd suggest using a period of 2 pi's instead of 1, and then using sine and cosine in radians in Niagara, and you're good to go. Now that vertical offset only is the actual wave height if the water plane is at 0 in Z in world space, and it's possibly not at 0. So when I do export that wave normal and wave height here, I may want to add the water altitude to convert that vertical offset to the actual wave height in world space, which can be done in many ways. Most likely you'll want to create a Niagara parameter collection and have a simple float parameter that you can update in Blueprint and sample in all your Niagara emitters, like so. Or create a material parameter collection, that way you can also access that water altitude value in your materials if you ever need to, and link a Niagara parameter collection to it. That's the approach I chose to use for my system, that way I can just update that material parameter collection in Blueprint, and the Niagara one is automatically updated as well. But I guess you could also assume this value is exported as an offset and account for the altitude later on in Blueprint. And really, when it comes to the Niagara side of things, that's all there is to it. The rest is done in Blueprints. Before moving on to blueprints though, I just want to show a few other examples, because I feel like this part here is the only bit that could really cause any confusion, so I want to make sure it's crystal clear. So let's check the second demo level, which uses Gerstner waves. That is a simple water shader that uses custom HLSL code to generate waves based on a number of parameters. Parameters that all come from a material parameter collection. I then have a Niagara parameter collection linked to that material parameter collection, that way I just have to worry about updating the material one. And I use that Niagara parameter collection in this Niagara readback system here to get those Gerstner waves parameters, right? And using the same exact HLSL code, I generate the same exact waves, and so at that world position, I get the same exact wave offset and normal. The only thing that differs when using HLSL code in a material and in Niagara is the way output pins are handled. In materials, you return the default pin value and you write additional output values. In Niagara, you don't return anything and write all output values. And that's pretty much it. Things may also differ ever so slightly when sampling textures and making use of specific interfaces, but all in all it's extremely similar and that's great. Now there's an elephant in the room, and it's something I already mentioned in my Gerstner waves video, but just to be sure, let's go over it one more time. A Gerstner wave is a mathematical formula that outputs an XYZ offset, so you cannot just sample the wave height by taking that offset's Z component. Because sure, it's the wave height, but offset in X and Y, so not the wave height at the world position you asked for. The solution then is to use an iterative approach. Sample wave the first time to get that XYZ offset, then sample wave the second time, this time shifted by the inverse of that first XYZ offset. Rinse and repeat, and within 3 or 4 iterations you get the wave height at a world position close enough to the desired world position. Hopefully that made sense. Okay, let's check the third level real quick. This material samples the height flipbook to drive the water displacement. And you guessed it, in Niagara I do the same exact thing. So if I have some kind of world position based logic to build UVs to sample that flipbook texture, well, I do the same exact thing in Niagara. Use the particle's world position, build the same exact logic with the same exact nodes, then sample that flipbook texture, and voila, it matches. So any water shader you can come up with, make it based on world position, then build the same exact logic in Niagara using the particle's world position, and voila, you should be able to use this buoyancy system with your own water shader. Cool. Moving on, at this point, this Niagara system sends that sampled wave height and normal to this blueprint per particle, so per pontoon. In blueprint then, first order of business is to get that pontoon's position in world space. However, I'm going to assume the user has set up pontoons with the mesh already scaled as desired, so I actually don't want to take this mesh scale into account during that transform, which can be done in many ways. Here I'm just going to counter the scale applied during that transform with an inverse scale first. Then compare the wave height at this pontoon with its actual position in Z to get how much that pontoon is above or below the water surface, right? Then clamp that depth based on that pontoon's diameter, so let's assume its radius is 50, that'd be 50 times 2. Next, well, most buoyancy systems are actually quite simple and rely on spheres to compute how much buoyancy force to apply because it's super straightforward to do, and this system is no different. The buoyancy force you apply can be simplified to equal the amount of water displaced by this pontoon sphere, which is a third of pi times the depth squared times 3 times the radius minus the depth. That's this pontoon's submerged volume. Now let's try to add this as an upward force at this pontoon's location and see what we get. Okay, it's a start. At this point, implementation may vary, but the idea is pretty much always the same. To have a buoyancy simulation that is, say, more stable, you have to add some amount of drag, both vertical and horizontal, as well as angular. And sure, you could rely on this object's linear and angular drag settings to do the job, but that would apply that drag at all times. And ideally, especially if you have some kind of high-speed boat that bounces against waves and can be airborne at times, it'd be nice if that high amount of drag was applied only when the boat is in water. And so you likely want to compute this drag yourself directly in the buoyancy system. So all in all, the secret is to generate lots of buoyancy forces, but also apply lots of drag. There are many ways to compute drag though. I tried my own custom method, but it was a bit finicky to fine-tune. Eventually, I ended up just copying UE's math. Simply put, the more vertical velocity in water, the more force it adds in the opposite vertical direction, kinda like a brake. Same for horizontal velocity, the greater the speed, the more quote-unquote brake force it applies. Angular drag is even simpler, it just adds the inverse of the current angular velocity multiplied by some factor. And that's it, it really isn't anything too complicated. There's no trigonometry, there's no call to expensive functions, the math is really straightforward, but sadly it just results in a lot of nodes. And this is called for each pontoon for each actor to simulate. So this entire code may easily be executed say 100 times per tick if you have a couple of boats on screen, right? And unfortunately that's when you do pay for the blueprint virtual machine overhead the most. For loops with many nodes is the worst case scenario for blueprints, and so on my hardware, doing this for just 7 pontoons seems to cost around 0.6 to 0.7 milliseconds on the CPU, which is quite a bit. Now, I don't have a beefy gaming CPU, I have a 1st gen Threadripper, so it's quite dated already, but still, I hardly expect this solution to be scalable even on modern hardware. The good news is that converting this to a C++ function is super easy and would massively improve performance. At one point, I also tried to compute the buoyancy force directly in Niagara, which would be way cheaper. That way I could just keep most of that blueprint logic and just apply the buoyancy force computed in Niagara. Unfortunately, that turned out to be a dead end because it proved to be extremely unstable at lower frame rates. I'm still unsure why exactly, looks like that 1 or 2 frames delay you get from that asynchronous readback causes no issues when just reading the wave height, but is problematic when also computing the buoyancy force to apply. Anyway, yeah, that's pretty much it really when it comes to this buoyancy system. Now, the next step is likely to move this logic into a component that you can add to any actor you wish to be buoyant. Which is exactly what I've done with my system, right? It has an enable buoyancy function, which first checks if the owner implements the blueprint interface needed to get the simulated primitive. Then enable physics on that primitive, get pontoons, spawn the specified Niagara system and attach it to that primitive, update and reinitialize that Niagara system like I previously showed, then start ticking. On tick, I may then want to first process that snap onto the water surface event, else just compute and apply buoyancy for each pontoon. There's one important detail though. Upon disabling buoyancy, it's highly likely I'd want to destroy that Niagara system this component spawned for its owner, right? The thing is, a component may only be destroyed by the actor owning it, so not this component, but whatever actor this component is added to, right? Also, there's a chance I might not want to destroy it after all if I expect that actor to be buoyant again in like 2 seconds. Which is why a reference to that Niagara system is kept around, so I can skip spawning one upon enabling buoyancy if the one previously spawned still exists. And so my point is, upon disabling buoyancy, I'd broadcast that event and forward that Niagara system. Then it's up to you to choose if you wish to destroy it or keep it around, right? It likely has a very small memory footprint, but shouldn't cause any performance concern since it's paused. So I'd say that's the one constraint you have to be aware of with this component-driven system. Okay, last thing I may briefly mention is that snap to water feature. It basically uses a gradient descent method to find the best fitting plane given a bunch of points, which is also a project available on my Patreon and a subject of a previous video on my YouTube channel. So the idea is the following. I get the first wave height sampled at those pontoons, and using that best fitting plane algorithm, I find the best location and normal to place and orient the buoyant actor so that it's ideally in a somewhat resting state already when buoyancy is just started. I suppose one other potential solution would be to see those pontoons as vertices and thus build a list of triangles. Then compute each triangle's normal and average all normals to derive a rotation. But then I guess there are a million of solutions to this problem, math is really not my strong suit. My approach seemed to work well enough, so I stuck with it. And that's how I built a custom buoyancy system using Niagara and blueprints. Now again, I consider it to be quite experimental. It certainly seems to perform decently enough to be shippable if you keep the amount of buoyant actors at any given time low enough, but there's other things to consider. For instance, I'm still unsure how well it scales considering I do spawn one Niagara system per buoyant actor. The asynchronous readback cost seems to be pretty much negligible for such a low amount of particles, but does it scale well with many systems around? Seems so, but again I haven't battle tested this system that much. I also experimented with a quote-unquote unified system where I had one single Niagara system that handled all pontoons for all actors. But then it was really complicated to keep track of which pontoon was attached to which actor and manually handle the local to world transforms for all actors. Here, having one system per actor, since it's attached, you can work in local space and super easily do the world space transform, so it's much easier to work with, But yeah, there are many things to consider still. Turns out building a complete water system is hard. Who knew? Voila, that's it for today's video. Stay tuned for episode 2 coming up very soon. I'll dive into my scene capture driven foam system. In the meantime, if you want to get your hands on this Buoyancy system, it's available as a tier 2 reward on my Patreon. Please note that it's just a Buoyancy system and doesn't include this finished project. This one will be released at a later date. Regardless, you're more than welcome to join my Patreon if you want to support me and see more content like this. Also, please consider leaving a like and subscribing to the channel if you liked this video. I also want to thank all my patrons for their ongoing support. I appreciate you all. That's it, I'll see you in the next video. Take care of yourself. Bye bye!